Welcome everyone. Today we're going to take a look at intersections of lines and planes in 3-space. So there's 3 options that we can have for how a 3D line can intersect a plane. And that would be that they intersect at one point, so the line just kind of crosses through the plane. They could have an infinite number of solutions if the line is actually on the plane or in the plane, I guess we could say. And it could have no solutions if the line is parallel and distinct from the plane. Now, if the line lies on the plane, we would call that parallel and coincident. So in both of our second cases here, we could do a check for parallel. And if they're not parallel, then that plane, because it extends in all directions, and the line, because that also extends in all directions, need to cross at some point at least once if they're not parallel. Okay, so when we go to solve, I'm going to show you all 3 of these cases. And when we go to solve, the process is actually a lot easier than when we solve for intersections of lines. So if I have a line that already is in parametric form and a plane, I can simply take my x, y, and z of my line in parametric form and plug those into the x, y, and z of my equation. And what I'm looking for here is whether I get a true statement, an untrue statement, or whether I get an actual solution for t. And all of those are going to tell me different things. So we're going to sub the line into the plane. And that means that I'm going to take my x parametric equation, 5 plus 2t, plug that in for x, and same thing with y and z. Okay, now our job is simply to expand and simplify and see what happens. So we're going to bring the 9 in, the 13, and the 2. So this is what you should get. And then we're going to simplify all of our constants and bring them over to the right side, and all of our variables here. Okay, so when we simplify the variables, we should get negative 53t. And when we simplify the constants, we'll get negative 24. I'm going to bring that over to the other side here so that we have 53 on the right-hand side. And that's going to mean that t is actually equal to negative 1 here. So if t is equal to negative 1, we can plug this back into the equation of the line, and that will give us the x, y, z coordinate of our point of intersection. So we're going to plug t equals negative 1 into the line. And like I said, if we get an actual value for t, that actually means that the line intersects the plane. And then the other options are we get an always untrue statement like 0 equals 8 or something like that. Or we could get a true statement like 0 equals 0. So those are the things that we're kind of looking for as we solve here. So we're going to plug that in, this, and for z as well. Okay, so we should get 3, 0, and negative 1. So that's our point of intersection. Okay, and again, I want to make sure that I'm using proper notation for this. So make sure that your point has round brackets rather than square brackets, because we're talking about a point of intersection, not a vector. So this is just a visual of what we just solved for, essentially. So you can kind of see how the line and plane intersect here. And basically they're intersecting kind of right at this point here, and that is the point 3, 0, negative 1. Okay, let's take a look at another scenario here. So same idea here. We're simply going to plug the line into the plane. And then we're going to expand and simplify here. So this is what you should get. And then we're just gonna gather all of our like variables here. So you might notice that you have 2 positive 6t's and a negative 12t. That's actually gonna give us 0. And then we have 4, negative 21, and negative 4. So what we're going to end up here with is negative 21 equals 10. And sometimes people will also like bring this over, let's say, and they'll say, okay, I have 0 equals 31. You can do that as well if you kind of want to leave like the t's on one side and the constants on the other side. But either way you do this, we do get an untrue statement. And as soon as we get an untrue statement, basically what you know is that these guys are parallel. And we also know that they're parallel distinct, which means that this line is actually never going to be inside this plane. So therefore, let's say the line and plane are parallel distinct, and that means that we have 0 points of intersection. Okay, let's see what this looks like visually on GeoGebra here. So here we have the line and the plane, and we can basically see from a lot of different angles here that the line is actually parallel with this plane. This is probably maybe the best angle that we can see that at, and that means that the line is never going to cross that plane. All right, and let's take a look at a final example of what you can expect to get if your line is inside your plane. So in this case, I'm just going to take a second and we're gonna make parametric equations if we don't have them already. So that would be this case. So always start by making sure that your line is in parametric form, and then we're simply going to follow the same steps. So you're gonna plug your line into your plane. Okay, one thing, just make sure that you put things in brackets because this negative, for instance, needs to go into both of those terms there. So just be mindful about that. And then we're going to expand and simplify. All right, so this is what you should get if you've expanded, and you should probably kind of notice here that you are getting 0 for t. And then when we take the constants and put them together, you're getting negative 12 plus 11. So actually what you get in this case is negative 1 equals negative 1. And we know that this is in fact always true. So if we get an always true statement like this, or a true statement just in general, that means that the line must be parallel and coincident with our plane. And what this means is that there's actually infinite points of intersection. Okay, let's take a look at what this actually looks like. All right, so here you can kind of see that our line is right coincident with our plane, so it's actually inside the plane, which means that I can continue zooming out here and that line is just going to be flush with that plane. So infinite points of intersection where that line kind of lies along the plane there. All right, so we should actually, given that there's only really 3 scenarios here, we should really be able to determine if the line actually intersects the plane or not by simply testing if they're parallel. And we can test if they're parallel by simply dotting the normal of the plane with the direction vector of the line. And if we get that the dot product of the normal of the plane and the direction vector of the line equals 0, that must mean that the line and plane are parallel. If they're not parallel, the line has to intersect the plane at some point. That's just how things work in 3 space, right? The plane is a really large flat surface that extends in all directions. So eventually that line has to cross that plane. So we're going to check the dot product. So here our normal of our plane is 3, negative 1, 1. And we're going to dot that here. So let's dot the direction vector and the normal. We'll get 3 times 3 plus 2 times negative 1 plus 1 times 1. So this is going to give us 9 minus 2 plus 1. So I think we get 8 here. So this means that the line and plane are not parallel. And that must mean that they have to intersect at least once. Okay, now of course this doesn't tell us what the point of intersection is, it just simply tells us that there is one point of intersection. Okay, let's take a look at another example here. So this guy, our normal is 4, 0, negative 2, and we're going to dot that with our direction vector. And I'm noticing here already that we're getting negative 8, positive 8, and 0, and that gives us 0. So therefore they are parallel. And basically we would just need to decide at this point whether they're parallel coincident or parallel distinct. And we can do that super quickly by just testing the point in our position vector here and seeing if we get a true statement in the plane. So we're going to sub in the point 1, 0, 1 from the line into the plane. So true statement means the point is on the plane, which means that the line must be in the plane. Untrue statement, the point is not on the plane, and that means that it's parallel distinct. So I think here we're getting 2 equals 11, and we know of course this is not true. So we are going to say 0 points of intersection because they are parallel and distinct. Okay, so I just want to show you kind of a visual of what we just figured out here in GeoGebra. All right, so this is our first example where we found that there was one point of intersection and we were correct. And basically what we were checking here, I've just graphed the normal of the plane with a scalar multiple to make it a little longer. But basically what we were checking is if the normal of the plane was perpendicular to our line, and we found that it was not, which means that that line must not be parallel to our plane and it must intersect at one point, which we can kind of see here. And then for our second example, we found that there were 0 points of intersection because these guys were parallel and distinct. So if we take our plane and we actually plot this normal here, I'll show you what this will look like. Oh, that would be negative 2. We can actually see that this normal and the line, this is probably the best view here, are actually meeting at a right-hand angle. And that's what we were checking with the dot product. So the normal of the plane must be perpendicular to that line if the line is parallel to the plane. So hopefully that visual kind of helps ground your understanding of what we're doing here.